This is 17.3 in simplifying radical expressions. If you have a square root of 4 and you multiply it by the square root of 25, that's the same thing as saying the square root of 4 times 25. So if you're multiplying two radicals together, you can just place them together. And then you can see that 4 times 25 is 100. And you know that the square root of 100 is 10. Because 10 squared, and the index is 2, and so the index and the squared canceled out, and you get 10. You're probably wondering why you would want to do it that way. Since you know this is 2 and you know this is 5, why wouldn't you just go 2 times 5 equals 10? You would on this problem, but let me show you problems where you wouldn't see it so easily and you'd want to multiply them together. So something like this problem, you would want to go ahead and just simplify the radicals separately because that would be the quickest. But on a problem like this, if you have the square root of 5 times the square root of 25, or let's take 20, sorry. If you have the square root of 5 times the square root of 20, the square root of 5 isn't a perfect square, neither is the square root of 20, and so it's not easily as seen. The answer is not easily as seen. But if I write it like this, 5 times 20, then you can say, well, that's the square root of 100 because 5 times 20 is 100, so that's 10. You can quickly see that the answer is 10. From this view, you can't really see the answer is 10, but once you multiply them together, you can see that they did come from they do make a perfect square. And so that's more of what we're looking at when we want you to understand that you can multiply radicals together. The reason why you would do that in some cases is because you don't see that together they might make a perfect square. So if I take the cube root of -3 times the cube root of 9. Now remember the index is that little 3, and so the cube root, you want to think of something that multiplies times itself 3 times. Well, the -3 and the 9 doesn't really help you, but watch what happens when you multiply them together, because you know that if you have a radical times a radical, you can put them underneath the same radical and multiply them together. Well, 9 times -3 is -27. So all I did was multiply these to equal here, changing the form, and now I'm going to change the form again. I know that if I have an index of 3, I'm looking for what can I take to the third power that will equal that -27. Okay, so -3 to the third power equals -27, because -3 times -3 is positive 9, then times a -3 is -27. So I know that the answer to this one, if I think about what you learned on the last section, the index of 3 cancels with the exponent of 3, and you get -3, and that's the final answer. Even sometimes you can have fractions, and the radical goes all the way down and all the way up. That's the same as having the fourth root of 1 times the fourth root of 3. So you can separate them out. The reason you can do that is because that radical goes all the way down and all the way up. And sometimes it's easier to separate them out. You can simplify them easier. So if I take a problem like this, if I say the fourth root of 1/3 times the fourth root of 1/9, because I can multiply radicals together, you just learned that at the beginning of the lesson, I can say this is the fourth root of 1/3 times 1/9. Well, that's the fourth root of 1 over, whoops, what am I doing? Where am I here? Oops, I messed up on the problem. Let me start over. Let me actually write the problem down right. Okay, sorry about that, you multiply it by another 4th root of 1/3. You can multiply all those together and keep them under the one radical. So 3 times 9 times 3 is 81, and 1 times 1 times 1 is 1. So I have the 4th root of 1 over 81. Well, that's the same thing as saying the 4th root of 1 over 3 to the 4th power, right? And I can take 1 to the 4th power, and it's still 1. And so now it's nice because my index and my exponents are the same. They're going to cancel out, and I'm going to get 1/3. Okay. I know you can do this in your calculator. When you do use a square root in your calculator, there's usually a button that looks like this, and that will allow you to change that index. If you're putting fractions into your calculator, make sure that you are putting them in parentheses. That will tell the calculator that the square root comes all the way down and all the way up. Okay, if you're not sure how to use your calculators on that part, you can always give me a call, tell me what kind of calculator you have, and I can look it up on the internet and help you through it. The reason why you're not using your calculators for these, you're probably going, well, I'll just plug this into my calculator, it'll be a heck of a lot easier. You still have to understand it because we're going to use variables. Like if I took the 3rd root of A and I multiplied it by the 3rd root of B, you need to understand that that's okay to say the 3rd root of A times B. Or if I took the 3rd root of A and divided it by the 3rd root of B, that's the same thing as taking the square, or the cubed root, of A over B. So basically this is the part that I want you understanding right now. So let's try a few other examples.
Do you want me to wash your cup, or?
If you take the square root of x times the square root of x cubed, you can think of those as the square root of x and then 3 more of them, because this x cubed means 3 of these. So if you think about it that way, if you combine these radicals, then it's easier to see that that is actually x squared squared. Now remember that the index on a square root is automatically 2. So the index and the squared will cancel. And you'll get x squared. Here's another problem. Sometimes you just need to look at them all laid out as much as you can. Like, let me show you. So like these two. You can't take a cube root of 2 and you can't take a cube root of 5. They're not perfect cube roots. But if you put them together, 2 times 5 is 10. And you have a squared. And now that one, and they have some in the textbook where, this one came out of the textbook where you can't go any farther here. There's nothing that I can do with 10 and a squared to rewrite it with a cubed root. So that one is as far as it would go. There are ones that we take farther later in this session. Try this one. I'm just taking these out of the book. They had the square root of 11 times the square root of xy. They were trying to show you that if you put those together, square root of 11 xy, there's nothing that I can do. That's an index of 2. There's nothing times itself that equals 11, and I can't do anything with 1x and 1y, so then I can stop on those. So we've talked about how the radical can include a fraction. So if I have 2x over y and a radical of 5, and I have 16y over x. If I put those together, I might start seeing things that I can do. It's hard to see when they're not together. So together that would be 32 xy over yx, which I'm going to write it xy. I'm just going to try to keep the same. So all I did is I multiplied these two together, and then I multiplied these two together to get that. Okay, so now if I take a look at it, these x's will cancel and the y's will cancel inside that radical, and I get 5 square root 32. And now you want to make sure that 32 can't be rewritten with a power of 5. So like maybe say, start with 2, and then if that doesn't work, 3. So 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times another 2 is 32. So that I can rewrite as 2 to the 5th power. So if my index is 5 and my exponent is 5, then I know the answer is 2. So sometimes you don't see it from the original problem, but if you start putting them together and then breaking them back down, then you start to see what kinds of things you can do with it. This next one, 16, whoops, it doesn't really look like a 16. 16, a to the 8th, b to the 18th. There's one like this on your homework. Bring that radical over. So I know that the index is 2. So if I could write these in powers of 2, that would be good. So I'm going to try to write them in powers of 2. So what times what makes 16? Well, that's 4 squared. So that'll work. Then a to the 8th, that's 8 a's. If I want them written in 2's, then there'd only be 4 of them because there'd be pairs. So I can write them as a to the 4th squared. If you're not understanding that, 2, 3, 4, 5, 6, 7, 8. There's the 8, and I want it in an index of 2, so I want it in pairs. So there's 4 pairs. Okay, so b, if I want it to be a power of 2, but I know it has to be this 18, then I know that this must be a 9, because 9 times 2 is 18, and you learned a long time ago about the power to a power. You can multiply them. Once you get all that written in powers of 2, then remember that the index and the powers of 2 cancel. So it leaves me a 4, a to the 4th, b to the 9th, and that becomes my answer. Let's bring in some things from a couple chapters ago. I can also have a trinomial, and maybe have a radical at the bottom. There's ones like this on your homework, and there'll be ones like this expected on the final. Well, I still want to look at, can I break this inside down to be something in the power of 2? So I'm going to look at how that breaks down. If I want to factor that, I know that it has to be something that adds to 12 and multiplies to 16 or to 36. So that must be 6. So I can take this. I'm going to put a 2 up there, and I know this is x plus 6 times another x plus 6, and I still have the square root of x plus 6 on the bottom. So I know that I can write that as one big huge square root, and I know that x plus 6 over x plus 6 is going to cancel. So that leaves me with the square root, and again, I don't need the 2 there. I'll erase that. They don't usually do that. And I have an x plus 6 left over. And that's as far as I can go. I can't break x plus 6 down into anything else. One thing that you need to notice is, let me rewrite this on the other page, this, and you want to make sure you understand this. This does not equal square root of x plus square root of 6. If you have this, x times 6, that does equal square root of x times the square root of 6. But it does not, that rule does not apply if there's addition in there. So that's huge. Here's another one. What happens when they're not perfect squares? We can still break them down even farther. Like if I say 300, think about what I said about them breaking down. And you can have, you know, 2 square roots. Oh, there goes my dog. Sorry. Sorry, new dog. What times what makes 300? Think about what times what makes 300 and you want a perfect square. Well, 100 is a perfect square. You know that. And 3 is not. But you know that 100 times 3 is 300. So I could break the square root of 300 into 2 parts. So kind of like backwards of what we were doing before when they were broken, when they were already in 2 and we put them into 1. This is a times sign in between. So I know that the square root of 100 is 10. But I can't do anything with the square root of 3. So I just leave it. Now some of your calculators, there's different modes. And you can put them in a mode that when you type in square root of 300, it will give you 10 square root of 3. There's another mode that when you type in square root of 300, it's going to give you, you know, the 10 point whatever it is. It's going to give you the actual answer. These are 2 different modes. And I don't know what kind of calculator you have. If you know, again, if you give me a call, I could probably walk you through turning it to one or the other. Okay, you do need to know how to simplify them like this, though, for the final. So, here's another problem. What if you have 3 square root 16, 16 to the third, to the cube root? We'll try to break that down. Think about what you could break 16 down into that would be something that would be cubed. Well, 16 is 8 times 2. And you know 8 is 2 cubed. So if you rewrite it that way, you can see that these 2 would cancel. And you would get 2 for that one. And then this other 2 right here, there's nothing I can do with that one. So the only thing I can do is leave it in the radical. So the yellow came out. The yellow part came out, and this is what I got. And the red part did not come out of the radical. You'll get the hang of what kinds of things break down pretty fast. Like 8, you'll know that that's 2 cubed. If I have 54 and the square root, remember that there's an index of 2 there. Okay, so I want to know what times what makes 64, and one of them, it would be nice if one of them was a perfect square. So I start thinking about what times what makes 64. Well, 9 times 6 does. So I could rewrite it as square root of 9, square root of 6. Well, the square root of 9 is 3. So then I have 3 square root of 6, and that becomes my answer. The more you do of these, the easier it becomes. I know you're looking at 54 going, well, I could break it down a lot of ways. You'll learn what your perfect squares are, and you'll start looking for them. Take this one. 25 x to the 4th. You always want to think about what is your index that you're dealing with. Well, I'm dealing with an index of 2, so I want to break stuff down into squared. Well, I know that the square root of 25 is really 5. And the square root of x to the 4th can be rewritten as the square root of x squared squared. So again, this index and squared will cancel, and I'll get 5x squared. And that would be my answer. Now your calculator won't do it with variables in it. That's why you need to understand it with numbers first. Try this one. 32 n to the 3rd. Okay, always think about what's your index. My index is 2, so I'm looking for things with squared. What times what makes 32? That one of those factors might be a perfect square. Well, 16 times 2, and I could break this n to the 3rd down to n squared times n. Okay, well the 16 can be written as 4 squared times 2, and I have n squared and n. So Here's my squares that are going to cancel with my index. So I'm going to get 4 and an n, and those are coming from, let me highlight it for you. That's coming from this and from this. Okay. Then I'm going to say I still have a radical, I still have a 2 in there, and I still have an n. So there's my final answer. Okay, here's another problem. 2a, the cube root of 2a times the cube root of 4a squared b. Whoops, a squared, whoops, that's not supposed to be an exponent. A squared b. So I'm going to put them all together and then take a look at it. Because these are, the reason I can put them all together is because they both share the same index. Otherwise I wouldn't be able to. So I'm going to put it all under the radical of 3. So 2a, 4, a squared, and b. Now I want to think about writing things with cubed. So 2 times 4, this and this can be rewritten as 2 cubed, because isn't there 1 2 here, and doesn't 4 have 2 2's in it? So these can be written like that. Then the a's, if I have 1a there and 2a there, I can write them as a cubed. I don't know if this color coding is helping you, but then I have a b. Okay, so I still have the cube root. But now what's really nice is, here's my index, there's my cube, there's my cube. So I know those are going to come out. So I get 2a, and the b is still in the radical. And again, try them and pause it, try it on your own, and then see if you got it. At first these seem really confusing. Once you get the hang of them, they're not too bad. Okay, so what index am I looking for? I'm looking for an index of 2, right? So I'm going to write this x to the 7th in powers of 2. So I know that that's x squared, there's 2 of them, there's 2 of them, that's 4. There's another 2, that's 6, and there's 7 of them, so there's 1 more. So I'm writing them in powers of 2 because I want my index to match my exponent. So now these 3 come out, and they make x cubed on the outside of the radical, and I still have an x on the inside of the radical. Here's another one, 4, so let's use the index of 4. And let's put a fraction in there. Okay, so I'm looking to put things in powers of 4. So the 16, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So I know that I can rewrite 16 as 2 to the 4th. I can't do anything with x cubed because there's no other x's, and I can't do anything with the y. Well, the y was already in the power 4. So now I can take a look at what's going to cancel. My index cancels with my exponents, leaves me with a 2 and a y as a fraction, and then I still have x to the 3rd inside the radical. Okay, here's one. There's ones like these on the homework and on the final test for the quarter. I could have wrote this all under the same radical, right? 1. Okay, so I'm going to look to break things down. Now factoring this, I'm not going to get cubes, am I? But I'm going to factor it and see what it looks like. It can't hurt to take a look at it in different forms. So I want something that adds to 3, multiplies to 2, that's 2 and 1. So I know that's x plus 2 and x plus 1. And I know I have cube root. And I know I have the cube root down here of x plus 1. So I'm going to rewrite this. and put this all over one radical. There. Okay, if I do that, you can see inside the radical, x plus 1 can cancel with x plus 1. The reason I can cancel those is because there's multiplication right between them. If there was addition right here where my red dot is, I couldn't do this. Okay, so now I get cubed root of x plus 2 and I'm done. Okay, and let's see. Maybe another one. I'm going to talk about this, but this is not on the final, but there are 2 problems on the homework. And I tried to fix that, but somebody had already started the homework, and so once somebody starts it, I can't fix it. But square root of 5 times the 4th root of 5. Again, you do not need to know this for the final. If you just want to not listen to this, that's fine. You're going to get it in the next math class. On the homework, if you get those last 2 problems wrong, just send me an email and I'll adjust the score. Okay, but the square root of 5 is really 5 to the 1/2 power, and the square or the 4th root of 5 is 5 to the 1/4 root power. I mean 5 to the 1/4 power. And so because these are the same base, you're able to multiply those, or not, well, you're able to combine those. The square roots are still on there. So you're combining that, you're multiplying those. So you have the square root of 5 to the 1/2 and, oh, what am I doing? Sorry about that. You got rid of this because you turned it into 1/2. Sorry about that. So because you have the same base number, if you remember, like x squared times x to the 5th is like x to the 7th. You remember how you added these two? It's that same idea. So then you're adding 1/2 plus 1/4. So you get, let's see, 1/2 plus 1/4. You got to find a common denominator. So you get 5 3/4. And that ends up being, the numerator is your exponent, and the denominator is your square root, or is your index. So you get 4 to the 5 cubed. So you get 4 to the 125. Again, there's things we skipped in the book, and so this is going a little bit farther than you need to right now. You'll get that in the next class, and they'll support you a lot more and show you why the index of 2 is 1/2 in a exponent, and why the index of 4 is 1/4 in an exponent. And again, I apologize for having that on the homework, and when I look through the requirements for the final, it seems ridiculous to give you those on the homework when they're not on the final. So you will not see multiplying radicals with different indexes. So again, if you get those 2 wrong on the homework, just send me an email and I'll give you those 2 points back. All right, thanks.